Hello, today I will be showing this neural network that can detect people in an image, which I made for a school project in which I collected data about the number of people in a room and then compiled some graphs, which I will show later on in the video. I used a convolutional neural network, or a CNN, for this project. It has 13 convolutional layers and 8 deconvolutional layers. It takes in an input image with a resolution of 1024 by 1024 pixels, and it's RGB, so it has 3 channels. And it outputs a 256 by 256 pixels image, which has 5 channels. The first channel is basically a mask, so each pixel has a value from 0 to 1, 1 being there is a person there, and 0 meaning there is no person there. So you get sort of a mask. As you can see, the black contour of a person sort of shows that. Then the other 4 channels are coordinates for the bounding box. So each pixel has coordinates for bounding box. The second, third channel are a vector pointing to the top left corner of the bounding box, and then the fourth and fifth channels are coordinates of a vector pointing to the bottom right corner of the bounding box. For the dataset, I use the crowd human dataset. It contains around 15,000 annotated images. These are some examples from the dataset. So it's just images with people, and then the annotations contain information about the coordinates of the bounding boxes for each person. These are the loss functions I used to train the neural network. I used 2 different loss functions, binary cross entropy loss, or BCE loss, on the left, and L1 loss on the right. I used BCE loss for the mask, which is the first channel of the output image, where each pixel should be either 0 or 1, where 0 is there isn't a person in that pixel, and 1 being there is a person in that pixel. So how it works is you can see the equation below the graph of BCE loss. P is the target, so that's what we get from the data set. That's what we want that pixel's value to be. And then Q is what the neural network actually outputted for that pixel. So we're trying to get Q to be equal to P. So if P is equal to 0, meaning there isn't a person, the left side of the equation goes to 0, and we're just left with log of 1 minus Q, which is the blue line. And using gradient descent, it optimizes Q, and it tries to get Q down to 0 so that Q is equal to P. But if P is equal to 1, meaning there is a person in that pixel, it's the opposite. The right side of the equation goes to 0, and we're just left with log of Q, which is the red line. And in this case, using gradient descent, it optimizes and tries to get Q to 1 so that it's also equal to P. The reason there's a negative, the entire equation is negative, is just so that the functions are flipped rather than going the other way. And then L1 loss I used for the bounding boxes, so it's the other 4 channels, it's the coordinates. This one's a lot more simple. Again, you can see the equation. P is the target, and Q is what the neural network actually outputted. The equation is just the absolute value of P minus Q, because when both the coordinates of the target and the coordinates of what the neural network outputted are the same, that's what we want, and then the loss is equal to 0, which is the most optimized. So this is what the equation looks like on the graph, and it just, again, uses gradient descent to try to get the loss down to 0 so that the target is equal to what the neural network outputs. And in the top, you can see the full loss. This is just a combination of the 2 equations I just explained, but it runs each of these equations for all of the pixels in the output image and gets the sum for the loss. And also it multiplies each of the losses by a weight. This is done so that if one loss is a lot smaller than the other, we can increase the coefficient of that loss so that it's about the same as the other loss, so that they both get the same amount of attention in training. A large part of getting this to work was also the post-processing. I needed to somehow use the mask and bounding boxes in every single pixel to get 1 bounding box per person. This was especially difficult because since people are a lot harder to find than things like faces or just static objects, the mask was a lot more spread out. There were lots of different blobs, so I couldn't use the same algorithm that I did for my previous neural network that could detect faces. In the faces, it was pretty consistent. There were just one blob per face. Here you can see there's a lot of blobs scattered around my body, so I needed to somehow convert all of those blobs into one bounding box. So this was the first iteration. This was basically just the same algorithm I used for my neural network that could detect faces. It found all the blobs of the green pixels, which is the first channel of the output image. And then for each of those blobs, it got the average bounding box and then just drew those. But this is an issue because, as you can see, there's a lot of different bounding boxes for one person. And this was bad because the whole point of this project was to be able to count the number of people in a room. So this was not ideal. So I moved on to a second post-processing algorithm. This algorithm added on to the previous algorithm. So after finding a bounding box for every blob, it would then look for overlapping bounding boxes. If two bounding boxes were overlapping a certain percentage, it would delete one of the bounding boxes. And this worked. It kind of merged all of the bounding boxes into one. As you can see in the video, it's pretty consistent. There's just one bounding box for me. The reason it's so jumpy is because I didn't take the average, but that wasn't important for collecting data because I was just wanting to count the number of people in the image. I wasn't concerned about the position or the size of the bounding boxes or anything like that. The issue with this algorithm is that people behind me, for example, would get filtered out. So if there was somebody behind me who was partially visible, their bounding box would be overlapping with mine, which would mean that either mine or their bounding box is going to get cut out, and it's only going to be registered as one person. So, like I said, this was for a school project in which I was monitoring the number of people in a room over 48 hours. So this is my setup. I used a Jetson Nano, which you can see in the bottom right. I used it to run the neural network and also do any other computing I needed to do. It's connected to a camera from which the Jetson Nano got video to run the neural network on. And also it's connected to an antenna to send data to the cloud, which I could then download from another computer. There's also a keyboard, mouse, and monitor. These are just for debugging, running the programs, and checking to see if it's working. And this was set up in a classroom. I set it up on top of a locker with the camera pointing down towards the room. Unfortunately, I couldn't position the camera in a way where it was looking at the entire room, so I just ended up looking at one table. So I kind of only ended up getting data about the number of people at this table. So it only really got up to 4 people, but I found that this was generally still good data to determine the general population in the room and determine the activity in the room. This is a line chart of the data that I collected. The way I was collecting data was I was counting the number of people over 10 minutes and then sending the average number of people throughout those 10 minutes to the cloud every 10 minutes. So this graph is representing the average number of people in the room every 10 minutes for 48 hours about. So as you can see, the y-axis is the number of people, and then the x-axis is the date and time. I labeled what these spikes might have been. So there's things like classes, night crew, teachers, after-school clubs. And it's really interesting to see because it actually matches what was happening in that room during that time, and I can actually get a good sense of what's happening in the room. These are the other two graphs that I made using the same data. The first one is the average number of people in the room during school hours and non-school hours. So the y-axis is the average number of people during that time period, and then the x-axis, obviously, school hours and non-school hours. So as you can see, it makes sense. There's a lot more people during school hours than there are non-school hours. The second graph is the number of people per period. So my school has periods A, B, C, D, E, F, G, H. So I was able to see during what periods are there classes. So this wasn't average, this was cumulative. So I just counted the number of people throughout the room during that time, which was every 10 minutes. And it's really interesting to see. You can actually see at what times there's classes in the room. So that's like A, B, F, G, H, where it's pretty large values. And then also you can just see if there was like one or two people or a bit more walking in the room during that time, which is D and E classes. If you're interested in looking at any of the code or any other details about this project, I will link my GitHub with this code in the description. And thank you for watching.